What's going on, math people? All right, we're back again, and we're talking about the limit of a function and limit laws. All right, so we have here the limit as x approaches x naught of f of x is equal to L. Well, where L represents your let look at this little piece right here. All right, so my graph is the diagonal line. So let me just toss something on that so that we're not confused of which one is the graph. Let me just toss this little greenery on top of that diagonal line. Make that a little bit thicker. All right, that's the graph. All right, so now when we're trying to find out what the limit is, all right, so this says as x approaches x naught. So we're looking at the values as x approaches x naught for your graph. The limit itself, if it exists, will be coming from the y-axis. It will be a y value. So let's look what happens as we approach x naught on this graph from the left. It's getting to L. All right, what happens if it approaches x naught from the right? Again, it's going to L. So if the limit, if you're approaching the exact same value from the left and the right, that is going to be your limit. If we would have approached a different value, let's toss in a different example right quick. Let's say we have new graph, and let's say we go something like, let's say we have it gets right there, and and right here. All right, and what we're going to go ahead and we're going to say that x naught is where I need you to be. X naught is right there. And we have up here, we have a positive L that we're reaching, and down here we have a negative L that we're reaching. Now let's do the same concept. As we approach x naught from the left on that graph, as soon as we get the x naught from the left, the limit is the positive L. But whenever we go from the right, the limit is negative L. Since you do not reach the exact same value coming from the left and from the right, then the limit does not exist. All right, that's just from the graphical approach. Now, let's say that we had some examples where it gives us equations. And the equation says, it says, find the limit of the function as x approaches some value. All right, let's say it like this. Before we jump into the example, ways to find the limits of equations. Limits of functions. All right, what we did up top was limits of graphs. Finding limits of functions. All right, shortcuts. 1, plug in a value. plug in the value, and that value is, it'll be x naught. Some text say x naught, some text say c, whatever the constant is. Plug in that constant value and see if you get something that exists. If you get something that exists and it's finite, hey, you found your limit. If it doesn't work, try factoring. Factor and simplify. Factor and simplify, then plug in. If that works and you get something that is concrete and finite, you found your limit. If neither of those work and you have radicals that are inside of your function, multiply by the conjugate multiplied by the conjugate expression. No, come on. In the numerator and denominator. All right, those are just some quick little tips. Now what I'm going to do is slide in an example of each of these and let us see what we're talking about. So the first example, let's say we have example 1. Example 1 is actually going to coincide with number 1 from our little shortcuts up top. It says, find the limit as x approaches 3 of, let's say, 3 times t minus 3 times t minus 4. All right, so when we find the limit, the first thing we'll do is plug it in. All right, so we're going to go ahead and plug it in. And what I mean by plugging it in is that value of 3. We're going to plug it into that expression there. We have 3 times the 3 that we plugged in minus 3 that we plug in minus 4. That gives us 3 times 0 times -1 equals 0. So the limit as x approaches 3 for that problem is 0. 0 is a finite constant, so that is our limit. All right, let's go ahead and toss in another example. Okay. Now let's say we have something like let's say we have the limit as x approaches 16. All right, I'll use 16. X minus 16 over x squared minus 256. All right, so first thing we're going to do, we're going to plug in and see if we get something that is finite. So we're plugging in, we have 16 minus 16 over 16 squared minus 256. This is 0 over 0. That is no, cannot do that right now. We haven't made it to that stage, so we're going to go into the next step. Step 2 says to factor and simplify and then plug in. So we're going to go in here and we're going to factor. So after we factor, we have limit as x approaches 16 of x minus 16 over x minus 16 times x plus 16. That's the difference of squares factorization. Alright, so that equals, alright, x minus 16 over x minus 16, that is reduced to 1. Oh, and I left out something that is very important. Limit as x approaches 16 of 1 over x plus 16. Now that I've factored and simplified, the next thing that I will do is plug in again. Now that I'm plugging in again, I no longer need the word limit right there. So we have 1 over 16 plus 16 limit 1 over 32. Boom, we have something that's finite that works with us. All right, we did an example of 1 and 2. Let's swing on down to the ugly of the ugly, that conjugate stuff. Okay, so let's see here. Let's say we have let's grab one that needs conjugate. Let's say we have the limit as x approaches 25 of the square root of x minus 5 over x minus 25. Alright, always try to plug it in. Plug it in. Well, y'all might be a little bit too young for that commercial, but anyways. So we're plugging in here, and every time we plug in, we have square root of 25. You do not drop the word limit until you start to plug in. And lo and behold, we have another explosion. Just like boom, 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 boom. No, that don't work. So we got to do the next step. Factoring that would be challenging. So let's multiply by the conjugate expression. All right. So we're going to go here. I'm going to identify the piece that contains the radical, and I'm going to multiply the numerator and denominator by the conjugate of that component that contains the radical. So I have square root of x minus 5, and the conjugate, change the sign. Everything's the same except the sign that separates the terms, over x minus 25 times the square root of x plus 5. So we did the same thing for numerator and denominator. We're going to go through and simplify. Alright, so multiplying the numerator, that gives us square root of x times square root of x is square root of x. Then we'll have square root of x times positive 5 minus square root of x times negative 5. So that middle piece cancels and leaves us with x minus 25 in the numerator. Alright, so we have x minus 25 in the numerator over x minus 25 times square root of x plus 5. Another simplification. Alright, we're not plugging in yet, so we still need to continue to have that word limit. and everything associated with it. Simplifying, x minus 25 over x minus 25 right there. And that leaves us with a square root of x plus 5 in the denominator. Now that everything has been simplified, we shall plug in, and therefore we no longer need that word limit equals 1 over 10. Oh yeah, back in the game. All right, so we've gone through those possibilities, and then there's some limit laws. All right, this is just a nutshell video, and there for you to be able to capture different components. All right, so let's run through some limit laws right quick. Running through these limit laws. All right, let's say we have two different functions. All right, limit laws. All right, so let's say we have the limit as x approaches c of the function f of x equals L. All right, so the limit for that one is L. Now let's say the limit as x approaches c for g of x is m. L, m, and c are all real numbers. Limit laws is straightforward. If you limit as x approaches c of f of x plus g of x, like we don't have to make this difficult, people. That's the same thing as saying L plus m. Just take the values, add them together. Same concept if it was subtracting. I'm just going to toss a minus sign right here. Everything else staying the same. That would be L minus m. Same concept if it was multiplying. We're going to ease on down. Toss in the multiplication symbol. It's not difficult. I promise you, it's not difficult. All right, and keep it rolling. Go ahead and toss in the division symbol. You already know. And then let's say we wanted to multiply our limit by a constant. Nothing hard about that. Let's say we have a constant k out front. K times the limit as x approaches c of f of x. That is equal to k times the limit as x approaches c of f of x, k times L. That easy. And here's another thing. That k can be factorable. That k can be right on the inside right there. That's k times, you get the exact same result. Boom. I know, too easy. All right, enough with the letters. Give us some numbers. This is a math class. All right, let me go ahead and find you some. Okay, let me go ahead and find you some numbers then. All right, so let's say we have key thing, right? In order for this to work, these guys must be approaching the exact same number. They can't be approaching different numbers. Okay. All right, so let's get us an example so we can wrap this thing up. All right, so we have the limit as x approaches 4 for the function f of x is 4. Now the limit as x approaches 4 for g of x equals -10. Problem says find the limit as x approaches 4 for f of x times g of x. You look at that, both of those approaching the same thing. You look at the limits, and the limits are 4 times -10, -40. Boom, too easy. That's it. That's all you have to do, and you apply the same thing for all of the other mathematical operators. Right? And just keep flowing. All right? Math people, until next time, hold it down, math people.